Welcome to VLSI lecture series. I, Professor Hitesh Dholakia, is going to explain you threshold voltage of MOSFET in this video. And I request you to go through my previous videos based on MOS and MOSFET so that you can easily understand this video based on threshold voltage of MOSFET. Now to explain threshold voltage of MOSFET, these are my session outlines where first we will discuss basics of threshold voltage of MOSFET. After that we will see parameters of threshold voltage of MOSFET. So there are total 4 different physical parameters which will be justifying threshold voltage. So we will discuss that, and based on all 4 physical parameters we will derive equation of threshold voltage for MOSFET. So let us begin this session with first agenda, that is basics of threshold voltage of MOSFET. Now see, before we go for a discussion, one should know what is threshold voltage of MOSFET. See, threshold voltage of MOSFET is a minimum voltage in between gate to source terminal, where after that voltage only MOSFET is having formation of inversion layer. So it is a minimum amount of voltage required in between gate to source terminal to form inversion layer. So you see the definition, it is a minimum voltage in between gate to source terminal which is required to form inversion layer, means channel in between source and drain. So without a formation of inversion layer, there will be no conduction in between source and drain. So you will have to apply gate to source voltage greater than threshold voltage, then only there will be a formation of inversion layer, right? So threshold voltage will defines operation of MOSFET. So if VGS is less than threshold voltage, then MOSFET will always stay in cutoff region. So to operate MOSFET in linear region and in saturation region, we will have to give VGS greater than threshold voltage. So here this gate to source voltage should be greater than threshold voltage. That is what the message that I want to convey to have operation of MOSFET in linear or saturation region. Now let us try to understand on which parameters threshold voltage of MOSFET is depending. So when we talk about parameters of threshold voltage in MOSFET, then there are total 4 physical parameters which will affect value of threshold voltage of MOS structure. So first is work function difference in between gate and channel. In MOS video I have already explained there is a work function difference in between gate and channel. At gate side there is metal and in channel there is substrate. So there is a difference in between work function with gate and with channel, that is resulting into threshold voltage generation. So this is first parameter. Second is gate voltage component to change surface potential. See, to have a generation of inversion layer, Fermi potential of surface that should changes from phi f to minus phi f for a generation of inversion layer, right? So this is second point which explains gate voltage component to change surface potential. In derivation you will get exactly what is this component, and already I have explained in a formation of inversion layer where Fermi potential that should change from phi f to minus phi f, right? So that is what the gate voltage component that will be affecting threshold voltage. Third is the gate voltage component to offset the depletion region charge. When I have explained MOS working with external bias, at that time I have explained when you apply gate voltage, at that time holes of substrate, p-type substrate, will move from surface to deeper inside of the material, and when it moves holes from the surface to deeper inside of the material, it forms ions, and because of those ions there will be a generation of voltage. So that is what the component which I have listed over here. So the gate voltage component which is generating offset in the depletion region, right? And that is because of ions which are generated in p-type substrate. And last is voltage component to offset the fixed charges in the gate oxide and in the silicon oxide interface. So when you fabricate MOS structure, at that time due to some imperfection in lattice structure, there is some fixed charges that is generating some potential. That is what the component which is listed over here. So there are total 4 physical parameters. One is a work function difference in between gate and channel. Second is gate voltage component to change surface potential. So here we need to change surface potential from phi f to minus phi f, right? Third is because of depletion region in which there are ions which is generating some potential, and fourth is because of imperfection of lattice structure during fabrication. So let us derive threshold voltage based on all 4 parameters. So that will be resolving your understanding furthermore. So now we will be deriving threshold voltage for MOSFET, and here I have listed 4 reasons. Now see, as per first reason, there is a work function difference in between gate and channel. So work function difference, let us say that is phi GC, and that is there in between gate and channel. If you have a gate which is made up of metal, then work function difference phi GC, that is phi F for substrate minus phi of metal. And if you have fabrication of MOSFET by polysilicon layer, then this work function difference will be phi F of substrate minus phi F of gate silicon. So this phi GC, that is a potential, right? So this is first potential phi GC. Now let us see what is second potential. So that is because of gate voltage component to change the surface potential. So see, for surface inversion, surface potential should change from phi f to minus phi f, then only there is a generation of inversion layer, right? So net change, that will be final minus initial. So final is minus phi f and initial is phi f. So total change will be minus phi f minus phi f, so that is 2 phi f. So this is second potential that is affecting threshold voltage. So first is phi GC, second is minus 2 phi f. Now see, as per third instruction, the gate voltage component to offset the depletion region charge. So as I have explained, when voltage is applied at gate, it repels holes deeper inside substrate and it forms depletion region. In this region, there will be ions which will be forming offset voltage due to charges of ions, right? And if you want to calculate that, then that will be as per surface inversion, where phi s, that should be equals to minus phi f, and that charge density that we can calculate as per QBO is equals to minus of square root of 2q Na epsilon Si into mode of minus 2 phi f. And I have already derived this equation. You just go through my previous video based on calculation of thickness of depletion region, in which we have calculated charge density at surface inversion, and that was as per this equation. So QBO, that is minus of square root of 2q Na epsilon Si, where this Na is acceptor impurity and epsilon Si, that is permittivity of silicon material, minus mode of 2 phi f, right? Now here, if substrate bias is given, which is VSB, then this depletion region charge density, that will change, where we need to add this substrate bias voltage with this minus 2 phi f. So now in case of substrate bias VSB, this QB, that will be now minus square root of 2q Na epsilon Si into mode of minus 2 phi f plus VSB. So this is what the case which we have given it for substrate bias. QBO, that is there with biasing voltage is equals to 0. But if you provide certain amount of biasing with substrate, in that case we need to add this substrate bias voltage over here. Now this is what charge density that we have, and based on this charge density we can identify potential. So potential will be QB divided by COX, right? And to nullify this effect of voltage, we need to apply minus QB divided by COX. Here QB divided by COX, that will be resultant voltage because of this third component. But to nullify that, we need to provide minus QB divided by COX, where COX is gate oxide capacitance per unit area. Now, fourth component of voltage that is happening because of imperfection during fabrication in lattice structure. So, because of that, there will be fixed positive charge density, that is QOX, and that is due to lattice imperfection at interface. So fourth component will result into voltage that will be minus QOX divided by COX. See, resultant voltage will be QOX divided by COX, but to nullify that, we need to provide minus QOX divided by COX. So now, as if you want to calculate threshold voltage, then that will be algebraic sum of all four voltage component. Phi GC minus 2 phi F, third is minus QB by COX, and fourth is minus QOX divided by COX. So here, for zero substrate bias, threshold voltage will be VTO, that is algebraic sum phi GC minus 2 phi F minus QB by COX and minus QOX by COX. And this is for zero substrate bias. If you want to calculate it with substrate bias, then instead of this QBO, we need to apply QB divided by COX. So threshold voltage with non-zero substrate bias, that will be phi GC minus 2 phi F minus QB divided by COX minus QOX divided by COX. Now let us manipulate this formula VT in terms of VTO. So for that, what I'll be doing is I'll be adding QBO divided by COX and I will be subtracting this. So see, here I have subtracted this and over here I have added this. See, minus minus plus. So that is this formula only. Now see, this is what VTO formula. So threshold voltage with zero substrate bias, and minus QB minus QBO divided by COX that we have. So if you rewrite this, then we can say VT is equals to VTO minus QB minus QBO divided by COX. Now, if you observe this term QB minus QBO divided by COX, then that we can calculate as per these two formula. QBO, that is minus square root of 2QNA epsilon SI into mode of minus 2 phi F, and QB, that is minus of square root of 2QNA epsilon SI into mode of minus 2 phi F plus VSB. So let us have this, right? In that, if you take 2QNA epsilon SI common, right, then you will be finding this is minus square root of 2QNA epsilon SI divided by COX, and into here QB minus QBO is there. So QB is having this component. So square root of this component minus QBO is having this component which is different compared to this. So minus square root of this component. So QB minus QBO, that is this as per these two formula. Now we can place this inside this equation. So we can have threshold voltage, that is VT is equals to VTO plus. Now see, this is what minus sign, but here we will be considering gamma as a plus of this. So that minus minus sign will get cancelled. So VTO plus gamma into this term, where gamma is this term, and that is even referred as substrate bias or body effect coefficient, where gamma is square root of 2QNA epsilon SI divided by COX. So this is the basic formula which is useful for solution of example, and based on this four parameters we can derive threshold voltage as per VT is equals to VTO plus gamma into this term. So this is all about threshold voltage calculation. I hope that you have understood this video. It is based on four parameters. One is due to work function difference. Second is due to surface inversion requires surface potential should changes from phi f to minus phi f. That results into change equals to minus 2 phi f. Third is due to when you apply gate voltage at a time there is a formation of depletion region, and that depletion region will forms ions which is resulting into offset voltage. And fourth is due to fabrication imperfection results into lattice imperfection at surface that generates potential which is minus QOX divided by COX. So that is how four different potential will result into threshold voltage, and that is what minimum voltage required to form inversion layer in MOS structure. I hope that you have understood this video. Thank you so much for watching this video. Please do give your valuable suggestions. The reason is your suggestions matters to me, and based on it in future, I'll be making videos which will be resolving your queries. So please do give your valuable suggestions. Thank you so much.